That's all. Okay. It's okay. So you guys can see my screen, right? Can any one of you confirm?
Yes, sir.
Yeah, and audio output is good, right? Uh,
Yes, it's fine.
yeah. Okay. Thank you. So let's begin with. Good evening to all. So this is a live interaction session for course of Aspen Plus Simulation Software, which is a basic course for the beginners, right? The purpose of this live interaction session is to have a one-on-one interaction of all of you learners with us TA, so that you can ask us doubts from what you have learned from the NPTEL recorded lectures. We can interact with you guys also. So the idea about this interaction session is such that what I will be doing is that initially, like say half an hour or hour, I will be giving a recap of what sir has taught. We will be doing some simulations in Aspen Plus, some problem statement or assignment we will be solving, and at the end we will follow it by a Q&A session, right? Introducing myself, I'm Bhavesh Moorjani. So I'm currently doing a Ph.D. at Department of Chemical Engineering, IIT Bombay, and I'm one of the TA. So there are actually two TAs for this course. I'm, and another person is Rajdeep Mukherjee. Right now what has happened for today's session only, like both of these slots of Rajdeep and mine are on the same time. But from next week onwards, what will happen that I guess Rajdeep is going to take the Saturday slot. So his session will be on Saturday evening 6 to 8 p.m. and mine will be on Tuesday 6 to 8 p.m. So you can join either of these slot depending upon your convenience. At the same time, this lectures are recorded. So even if you are not able to join this live interaction session, you can watch it later on the YouTube also. So that link, course link and the course content that we are teaching you guys, that will be available to you via that Swayam portal. So links will be generated there. So this is just a brief about me. As I'm saying, I'm working in I'm doing PhD at IIT Bombay in Chemical Engineering Department. I have completed my BTech from MS University Vadodara, where I was introduced to Aspen Plus course in my third year. Thus, I have opted for this TA work for Aspen Plus in this NPTEL course also. These are the contact details of mine. Like you can contact me from this. Okay. So before getting started with this lecture, I want to know uh, background of all of you guys. Like how many of you are from the BTech background? Can you raise your hand? Okay, so we got quite a few. 1, 2, 3, 4. And rest, are you from MTech or some other background? Or have you completed BTech and... Okay. So like I guess we have a mix of people. So can any of, if you want to voluntarily say why you have taken this course and what are your expectations from this course, so that I can know and design this live interaction session accordingly. Any of you can say it. Okay, it's no pressure. I guess we have shy people here. So I assume all of you have taken this course either to learn the Aspen, like specifically those of you who are doing BTech, to enhance your skill, to add it to your CV, or those who are doing it after their bachelorates. They want to again, learn a new simulation software for their job purpose or something else, right? We will be learning the simulation aspect of Aspen. So this course will help you to do a basic simulation, like basic process simulation in the Aspen Plus, how to use Aspen Plus to compute various properties, how to calculate You know, like process plant simulation, how to do process plant simulation in the Aspen Plus. A general guideline that I will tell you for you guys. Let's say if there is some connection issue and I get disconnected, please wait for 10 to 15 minutes in this meeting only. I will join again. Same thing if the timeout for this Google Meet link happens, do join on the same link again. We will continue from where we have left. Okay. So just wait for 10-15 minutes if any error occurs, right? So let's start with this course. I guess you guys can see the screen. Okay. So this course basically talks about the modeling and simulation aspect, right? So first, if these two terms come into your mind, what you consider modeling? Can any of you answer me? Like, what is modeling itself? Guys, I need active participation from you. You don't have to worry about being right or wrong. You can just say what you feel, what modeling is. Hello? Is it I'm clearly audible, right? At least you can say yes or no. Hello?
Yes, sir. Yes, sir.
Yeah, so don't worry about it. It's kind of an interaction session. That's why that says live interaction session. So you don't have to worry about being right or wrong. You can answer the way you feel it. Okay. So that way it will be more fruitful and useful to you. So any of you want to answer, like, what is modeling according to you? So let's say modeling is kind of a, you know, simplification of simplified representation of any system. It could be a complex system, it could be a simple system. So it will involve formulation of some mathematical equations to represent system behavior, or how system changes with various variables that are involved into the system. Let's say consider one example. I want to see how ice block melts. So let's say I have an ice block which is present in the room. Okay, then because of the heat transfer it will melt. Now what are the basic mode of heat transfer that you guys know? So we have three basic mode of heat transfer, which are that. So that is conduction, convection and radiation, right? So let's say we have an ice block which is present in the system. I cannot see my cursor. I think it should be. So yeah, let's say we have an ice block which is present in a room, right? So as I was saying that we have three mode of heat transfer present. Like one is heat transfer that will happen by the conduction. So ice block which is present on the surface, it will conduct heat through the surface. It will radiate the heat as well as it will have an convective heat transfer through the air, right? So if we write an equation like energy balance for that heat ice block, you can write it in this form, right? That heat transfer by ice block, that will be combination of forced, natural, conductive and radiative heat transfer. And we got a separate equation for all three, right? But either could it be forced convection or natural convection. We follow this, Q is equal to H delta T. Similarly for conduction and convection, so radiation, we have this equation. So through this such equation, like this representation of our system with such equation is nothing but a modeling. Okay, with the help of this model, now what we can do? So modeling is one aspect where we represent the system by different set of equations. And when we talk about the simulation part, so simulation is like utilizing these models that we have developed to predict the system behavior or its performance, right? And so it kind of involves running experiment on this model to understand how various parameters will affect. So let's say in this previous case that we have noted, we had ice block, okay, surrounding in the room temperature. So let's say room temperature is Tr. Now how rate we can compute how rate is changing with the temperature with time. We can get some profile, and based on that we can estimate how long it will take for ice to completely melt, right? So that is kind of a simulation. So simulation doesn't have to be a complex term. So that's what I'm saying, that modeling and simulation are very basic terms. So what happens, like any physical system, okay, that inspires a model based on the observation of physical system, like how it changes, like this all the models, that convective heat transfer, it was given by Newton's, right? So Newton's law of convective heat transfer, Q is equal to H delta T. So that are based on the observation, and based on that physical observation we develop a model, and that model is used to simulate a system behavior that can again give you how system is changing with various parameters. So modeling and simulation go in hand, and it doesn't have to be a complex part, like each and every aspect of your life involves kind of a model or simulation part. It could be a complex, it could be a simple thing also, right? So but how this modeling and simulation help us? So it will help us to analyze the system, predict the outcome, as we were saying, like if we want to calculate how much time it will be needed to completely melt this ice block, okay, so that we can predict the outcome, we can optimize the performance of our system. It can help us into the decision, it can help us in training and education also, like this course that we are doing in simulation. So that is what kind of a training and education. Then you, once you learn it, you will apply it to actual conditions. Like there are virtual labs also developed by different IITs to just kind of understand and get actual feel of how real experimental works, because you cannot always perform experiment all the time. Rather, if you have that model that represents your system present, you can do a modeling and simulations, right? So this term modeling and simulation goes hand in hand, right? Now coming to the how modeling and simulation is useful to us as a chemical engineer. So for chemical engineer, we deal with process plant simulations, right? Where we deal with various processes. It could be unit process, it could be unit operations, heat exchanger problems, distillation problems, scrubber problems, or reactions, right? So every one of this equipment involves some sort of a model associated with it. So this is a basic like example, like normal example of production of formaldehyde through oxidation of methanol, right? So this process involves kind of oxidation of methanol in the metal oxide catalyst at higher temperature of 300 degrees centigrade, and you get a conversion of methanol to formaldehyde, which is then again scrubbed into the water, and you get a formalin solution, okay? So this is a basic process that we know, but each of this component, like each of this equipment in this process flow diagram has its own set of equation that we have learned in our UG curriculum, okay? So can you guys help me to list all the blocks, all the equipments that are present in this process flow diagram? Can you just name one by one? Hello? Guess this is simple, you can just answer it. Like we have heat exchanger, then I have reactor. What else I have here?
Evaporator,
Yeah.
preheater,
Yeah, we have evaporator, then we have pumps, we have compressor. This is the reactor, this is our evaporator. Then this thing, this is a scrubber, or you can say absorber, right? And so these are the list of equipment involved particularly to this process flow, right? We have pumps, compressor, heat exchanger, reactors. Now when we are doing mass and energy balance, so you must have done this mass balance, energy balance calculation in your unit operation related subjects, right? So there we follow a set of equation for each of this. So let's say if I do a checklist where for each of the 6 equipments that I have in system, what kind of balances I need. So for reactor we will need both mass balance, right, as well as heat balance is also needed for a reactor. If I talk about scrubber, so scrubber we are putting water and formaldehyde is absorbed and we are getting formalin solution, so that is kind of a mass balance. As well as there will be heat exchange also between the cold water and this fume, which is like with product which is coming at 125 degrees centigrade. So heat balance is also there. For heat exchanger, do we need a mass balance? Yes or no? Hello. This is simple answer. You can say it.
No, sir.
No. So we don't need a mass balance in heat exchanger, but we need a heat balance, right? So that is MCP delta T of product. Sorry, tube side is equal to MCP delta T in the reactant in the cell side stream. Similarly for pump also, mass balance we don't need it. Since input is equal to output, there will be some leakages, but that is not our concern right now. So there, do we need a heat balance? This is also one question. Like for pump and compressor, we don't need mass balance, but do we need a heat balance? I'm putting it right, but is it like we do heat balance in pump and compressor? Have you heard it? Or what should we call it then? So in pump and compressor, we actually don't heat a system, but rather we have an energy balance. Okay. So in pump and compressor, you get energy balance, so which is kind of the same as in heat balance. So if I want to simulate a process, let's say I want an production of formalin solution around 10 ton per day, then if I want to know how much raw material will be needed, how much plant utility will be needed, I will be doing mass and energy balance across all these components, and then we'll calculate how much, and then I will calculate how much energy is required for pump, how much energy is required for compressor, or how much scrubber water intake is required, right? So these are the different calculations that we performed as a chemical engineer. But as I said, that models for all this equipment, like most of these equipments are available, like all the equipment that we have listed, even the some of the which are not listed here, like a distillation column or a flash drum. So that are already you guys have learned, and you know the mass and energy balance across the flash and distillation column. So that equations are nothing but a model. But then our task is to choose the right set of models and to simulate this process, like calculate this various properties. So for a small system, it is possible to do it manually. But let's say you have like for refineries where you have multiple complex involved in within the one plant only, multiple equipments, then doing this calculation by hand will become much difficult. So in that case, we will need some automation, right? So you might have done some automation of calculation in any of your UG curriculum or some lab course where you might have. So if I remember, we were doing this heat exchanger calculation in Excel. So like we were automating heat exchanger calculation where you put in the properties and then you get the output, desired output. So that sort of a thing you can do. So that is kind of a simulation part, like based on implemented mod like equations, we implement it in the Excel and then do a calculation. But when it comes to such bigger plants, we cannot do it manually. So in that case, we need some software, and thus this Aspen Plus kind of a software helps us. Okay. So what exactly is Aspen Plus? So first, Aspen Plus is a simulation software, like process plant software developed by Aspen Technology. So full form of Aspen is like this advanced system for process engineering. So this is the full form of Aspen Plus. And with this Aspen Plus software, what we can do, you get this different powers of doing flow sheet simulation, unit operations. You can calculate various thermodynamic properties, do sensitivity analysis. We will be learning this step by step. I mean, we won't be going all in with all this data. So as this course intend to introduce with the Aspen Plus and how to calculate and compute different parameters there. So we will be going one by one to all of this. Apart from that, there are other products of Aspen Plus also. So if you will search, like there are Aspen HYSYS, Aspen Batch Process Developer, or even Aspen Exchanger Designer. So if I just Google search it, like Aspen Plus, so you can see, you can download Aspen products from here. So there are various products like performance engineering. So you have Aspen Plus, Aspen Exchanger Design, which is specifically developed for design calculation of heat exchanger. You have Aspen HYSYS also. Do any of you know the difference between Aspen Plus and Aspen HYSYS? or have you come across this term before? Uh, I assume no. So the basic difference of Aspen Plus and Aspen HYSYS, you can consider it in terms of that Aspen Plus is more oriented towards steady state operations. So it's kind of a general chemical process plant simulator, while Aspen HYSYS deals with most of a dynamic processes, which are really time dependent and specifically catered towards refinery and oil and gas refineries, right? So it has more control and optimization parameter. So you can also check out the other products of Aspen Plus also. If you will go into the Aspen HYSYS, you can find the details of Aspen HYSYS. What are the what things you can compute it from. So Aspen is not the only software here, right? Apart from that, have you guys have heard this software DWSim? Yes or no? Yes. So
Yes,
if
sir.
you are answering in the chat
Yes,
box, it will
yes.
be better for me to at least. Again, I'm saying it's kind of an interaction session, so don't be worried about anything saying wrong. And this is also kind of a me doing first time this kind of interaction session. So again, it will be helpful for me also. So if you guys can give me a feedback, right? So relax. Uh, if you have a doubt, you can interrupt me also. If you think that I need to change some way of explanation, you can correct me. Okay, that's fine. So this DWSim is a freeware. Like Aspen Plus is a kind of a commercial software. So DWSim is a freeware, free process plant simulator. Apart from that, even for heat exchanger design, you might have heard this HTRI and ChemCAD kind of a software. So there are various softwares which are present to do this kind of a process plant simulations. And currently we are diving into the Aspen Plus. Okay. Here now, so uh, like how many of you have downloaded the Aspen Plus or installed the Aspen Plus? Because I have received the mail from NPTEL team today, so I'm assuming most of you have not gotten access to Aspen Plus yet, right? Or any of you have installed Aspen Plus in your system? Can you raise your hand if so? None of you have installed Aspen Plus yet.
Yes, sir, I have installed.
Okay, okay, thank you. Yeah. So I guess we have got this link today to download the software. So just check it out and fill it out. So you can install it and then you can explore the software by yourself only. So let me start with here. So I'm currently using my IIT Bombay's license for Aspen Plus. Once you get access from the NPTEL team, you can also use this software, right? So this is the version 14 that I'm using, and I'm assuming current version provided by NPTEL team is also version 14. So when you will open this Aspen Plus interface, you will get this kind of a screen. Obviously, if you have seen the second lecture of Professor Saha, he has kind of given a kind of overview of this initial screen where different things that you can do in there. Okay, so there are resources available where you can search different examples. What you can find what is the difference in various version of Aspen Plus, right? So parts I will be touching some aspect of it. So my goal here today is to kind of give you an guideline, like complete guide through of different Aspen Plus parameters. Okay, so that when you install the software, you don't feel unfamiliar to it. You will know, okay, which tab will give you what kind of property, from where you can compute different things. Okay, so let's go and start one new simulation. Now depending upon your laptop or PC specification, it will run faster or slower. Since I'm doing some recording also and presenting also, it might take some time, so bear with me. So yeah, it's loading. It's taking some time. Just give me a minute. Yeah. So meanwhile it's loading, let me go further. So in the first week of the lecture, what sir has dwell into is the how to compute different properties into the Aspen Plus. Specifically, what are the models available, and what are the property like different data banks available. So what I will do is I will kind of give you a general overview of what kind of model we can use. To answer you directly, there is no straightforward method of selecting models like this model will work for what, but rather you have to understand what each property estimation model does and how it computes various properties. Okay, so if you will go into the Aspen Plus, so there are basically this the six component data banks which are loaded by default. Apart from that, there are other component data banks also which contains the data of various like properties for various compounds. Okay, we will go into the details of that. And then let's say you have selected some compound. Let's say I'm selecting benzene and toluene. So that data will be, so when I'm entering the name of benzene and toluene in the compound selection process, it will go and search through this name into all six of the data bank and will give me the result, right? So similarly, if you don't have any compound which is present in this data bank, there are other data banks also that we can load it and search it from there. Once we have added different compounds, now for the calculation of various properties of this compound, we have to select a model. So there are basically four models. We can categorize models into the four parts as sir has taught. One is ideal model, equation of state model, activity coefficient, and other models. So what does it mean and how these models are useful? So first is this is the pure component data bank. So this is the screenshot from sir's lecture only. So you can see each data bank has some specific compounds available for its calculation. Like for pure 37, it's a kind of a general data bank which is developed by this Design Institute for Physical Property Data. Okay. Then for aqueous, you have pure component parameter along with ionic liquid and some molecules physics. Similarly for solid, inorganic, and some equation of state. And there are U's also mentioned. Now when we talk about the model selection part, So rather than just going into the theory, I want to discuss that in Aspen. Oh, now it's loaded. Yeah. So let's uh, dive into the interface of Aspen Plus, and again we will be discussing this property selection part also. So when you open the Aspen Plus interface, this is the first thing you will get. This left side you get a navigation bar where you can go to the different blocks and properties calculations, right? So when you start it, so here there are mainly four types of calculation: property estimation, simulation, safety analysis, and energy analysis. So mainly we will be dealing with properties and simulations. Okay, so first comes properties part, where in the properties part you have to select, you have this list of options that you can work with. So first is the setup of the system. So you can provide and title. So let's say this is kind of an uh, example simulation, so I can provide and title. You can write a description also. So there are unit selections also available. If you want to work with an SI unit, if you want to work with an English unit, or and so on. Let's say I want to work with an SI unit, since I'm more familiar with SI units, so I can select it from here only. You can give a description, brief description. So this example shows how to compute properties in Aspen Plus. Okay. Now this kind of thing for you it might not be useful, but when people are working with various projects, giving the date, name, description to the project becomes an important. And this other part is kind of related to some people which are working in the group. So that is a basic naming convention. Then first important thing comes is kind of a selection of the compound. So for the compound selection, as I was saying, so we have the data bank which is available. So here you can see there is one tab of enterprise database, where there are this database already preloaded. Okay, so as we were saying, there are basically 6 component data banks which are preloaded. So here pure 37, aqueous, solid, inorganic, APOS, NISTRC. So as you can see here, instead of pure 37, it's pure 40. Depending upon the version, the data bank will be get updated, right? And there are some others also that you can add or remove. Let's say I want to add pure 37, I can add it. Now when I say what are these different data banks available, like, but how to understand what exactly it is. So for that, just a minute. So when you get stuck into, like, when you are confused in this aspect, like which method means what, so just use this question mark button which shows an help. In help part, I can just search. So let's say I want to search what is aqueous. So I will search aqueous, and it will load it will search into the guideline, like this help book of the Aspen Plus, and you are getting first aqueous component data bank. You can open it. So so see here, you can see that what are the components involved. So the table below lists the component present in the aqueous data bank, and that component starting with the different name. So let's say I want to see a C1. So when I'm clicking the C1, which so you can see the different compound names which starts with the C1, like which comes under this category. Similarly, you can see with BA, so different compounds which starts with this. So what we had learned about this aqueous method. So aqueous pure component parameter for ionic and molecular species in aqueous solution. Okay, so specifically used for electrolyte. So if you are not sure whether your compound is present in this data bank or not, one way is directly search related to the compound. If you don't find it, then see all the available options, search into this data bank. Let's say I want to learn more about what are the inorganic compounds present. So search inorganic. So inorganic component data bank. So you can see various metals and everything are present. Okay, so metal and metal complexes which are present here. Silver complexes. So that way you can decide whether your compound is present in this database or not, or just you can start typing your name here, like typing compound name. Let's say I want a water, so I just write water, and what it will do, it will search water in this data bank, and when it will find it, it will add that compound here. Again, it's taking some computational power for me with this recording. Yeah, see, it has added water along with its formula, right? Apart from that, you can use this find button also. So as sir had explained that if your compound name is small, you can directly add it from compound ID. But let's say if you have a bigger compound present in the system, then you might have to do a search. Let's say I want to search compounds which involves benzene ring. So I can do this benzene and click find now. So it will search all the compounds which contains the benzene. I guess again it's taking some time because of me running multiple things. So depending upon your PC specification, it will run. It generally runs faster if you are not using something else, right? So you don't have to worry about performance issue there. Let me just do okay. It's not searching for some reason. And you can also customize your result, so you can specify different classifications, whether it's an aromatic ring, whether it's an ester, it's an carboxylic acid. So it will kind of do a filtering into the your search, uh, right? You can also specify the molecule weight, that start molecule weight from this to this boiling point range, and then it should give you the list of datas related to your search. So there are different in the name part. You can do a begin with benzene. You can search compounds which contains benzene in it, or you can just do an equal to search and search it. That's not happening. I'm writing it wrong. Let me do it here. Let's say if I want to add benzene and I do it. It's not responding. I guess because of the recording it's happening. Yeah, anyone want to say anything? Yeah, it has added benzene. Let's say I'm adding another compound also. And toluene. So write the name. If it can search it directly, it will add it. Else you can use this find option and you have to find it. once this is added, we can move to the property estimation part, and then I can show you what next we have to do. You have to use recording on some other part. So meanwhile, let it respond. So as I was saying that in order to know the data bank, like when you are using the software and you are not aware about it, like use this help button or search button and go to various forums to try and understand what properties and what methods to use. So as we will be discussing, like let's say we have selected this compound water, benzene and toluene. Now I can use ideal model also to calculate its properties, like what property we are talking about when we are saying that we want to use this model to calculate a property. So it is thermodynamic properties, so it could be the heat capacity of a compound, density of the compound, specific heat, latent heat of vaporization, such sort of a thing that we can compute from the ideal model. Also we have equation of state model. Also in equation of state you have this two models, cubic equation of state and virial equation of state. Apart from that we have activity coefficient model. So if you want to give a general classification, so this equation of state models are useful particularly for a vapor phase, if your compound is in vapor phase. And if you have a liquid phase which is let's say greater than 10 bar conditions, then using activity coefficient model will be a much useful thing, right? So let's say I'm simulating a system and I'm starting with an ideal model. So when to use an ideal model? So what are the conditions, under which conditions we can consider a gas as an ideal gas? Can any of you answer me? Like what are the conditions to define a vapor phase, like gas phase, as when we can consider it as an ideal phase? What will be the
For
temperature
ideal
pressure?
gas,
Yeah.
for ideal gas, we consider no interaction between the molecules.
Yes. So for ideal gas, we say that they have negligible volume as well as there are no interactions. And such conditions are valid for a low pressure and high temperature conditions. So if you have a gas system and you are working at low pressure values, you are working in vacuum and temperature is relatively high, then you can consider ideal model to represent your system. Similarly, let's say for the liquid. So again, what are the conditions to define a liquid mixture as an ideal? So that should be no change in volume when we are mixing a two liquid. Apart from that, what will be the other condition? If any of you know it.
Chemical potential zero.
No, it's not related to chemical potential. Rather, it will be that there will be no heat of mixing when we are like when we are mixing two liquids. They should not produce any heat. So heat of mixing should be zero, and there should be no change in volume. So that kind of defines the ideal condition for liquid mixtures, right? So and what kind of molecule will fall, like what kind of compound will fall? So compound which has around same size, that will fall into the criteria of ideal liquid models. So it has loaded, but it's not searched. I didn't found it. Oh, I wrote a wrong spelling. So see, I wrote a wrong spelling and it didn't search it. So if you will do it right, rename. You wish to rename it. Yeah. So now it has added the toluene also in the system. Sorry, again coming back to this part. So there are set of conditions that you have to define, like under which conditions we will take what kind of equation of state or what kind of model. So once you have added your compound here, if you will do this, so if you will look into this top menu bar, you have various options, uh, and when you don't know what exactly do after this, like after adding compound, you can just press directly next. So what this will do, it will take you to next necessary input required for your system, and then you can specify different inputs. So like this in between things which are not needed for us, like this assay and blend, so that is useful for if someone is doing crude oil analysis, where they can add this assay data. So assay data is related to the specification of various crude oils, right, if you know it. So for that, so but this is not needed for my condition. Right now I just want to understand and deal with this three component only. So you can just put press next, and it will go to the next required input, so that is in specification. For specification, as we were saying, that we need to compute. Now we have this compound with us, but in order to do this mass and energy balance, we will need various property of this compound, and for that we have to follow some method to compute this property at different conditions. So for that, there are basically like four types of method available: ideal, equation of state method, activity coefficient method, and the rest of the method you can categorize it in that way. So when you do it, like there are different options available here. Now I don't know, like you also, like you will be starting same way I am also starting, and I'm seeing there are multiple options in here, but I don't know all of this option, like which will be useful. So in that case, again use the help button to identify and eliminate different options, or you can also use method assist method also. So here we have this method assist menu available. So if I click in onto that, this page will open up where I can use I can specify component type, or I can specify the process type. Let's say I want to go by component type, right, and I want to simulate, I want to see water, like since we have water in our system, so there are various options. So you can see special, water only, amines, sour water, carboxylic acid. So for water only, what kind of methods are used? So here it lists different method, steam, TA, STAM, NBS, and there are various methods listed here. Now I want to understand which method will fit to my system best. So you can just go into any of the system, like click onto this data bank. So in here information is mentioned for this property method. So like this IAPWS 95 property method. Okay, so it uses this correlation. Okay, and there are various stuff mentioned, like how it will calculate the property. So you can see the error estimation, like estimated uncertainty for various properties are mentioned, range of the properties also mentioned. Okay, so lowest temperature to use this method is 251 Kelvin at 209 megapascal to 1273 Kelvin. So now you see, like we want to, let's say I want to do a simulation of water at a normal condition, then is it useful to me? No, right? So that way you have to eliminate this method. You can look into the other method also. So all of this method kind of, they are steam related, so most of them are high pressure methods, like the values are estimated at high pressure. So if you will see the details of each of this method, you will understand what are the range of these methods. If Aspen doesn't have it present in the help manual, you can also search it in onto Google, like simply understanding it, you can find the data of this method and understand where they have applied this condition. So what I'm seeing here is like most of these methods are related to the steam, like at high pressure condition, but right now I don't need it. So I can for current purpose only, anyway we are going to use an ideal method, but in a way you can eliminate this method also. Let's say you want to understand the equation of state method. So there are various equation of state method available, right? So you have Peng-Robinson equation of state. So just go to the question mark, help button, search Peng-Robinson. So when you will search Peng-Robinson, so first it will come up be like the result will come. Then you can see Peng-Robinson property method. It uses standard Peng-Robinson cubic equation of state. Okay, and if you want to go into the further details of it, you can click it here. You can find the equations associated with that model. What are the limitations and advantage of that model? Okay, see, there are lower limits and upper limits also mentioned for this TCPC data. And then you can see whether your compound fits into this data or not. So there is no specific right or wrong answer to which method you have to select, but rather you have to eliminate various methods. Even if we compare the, let's say we compare Peng-Robinson method with SRK method. So in that also, let's first you have to find that whether the property estimated by Peng-Robinson and SRK for your compound, does it deviate too much? If yes, then this property estimation method will affect your simulation result. If no, if that error between two method is, let's say, 1 or 2%, and depending upon your system it might be important or it might be very irrelevant. So this way you have to decide and eliminate various methods, right? So my initial assessment, like specifically those who are looking for this subject or use of this subject to work in this Aspen plus simulation direction, like working it more thoroughly into this direction, is to dwell into this various properties and understand it. So for right now we will just select an ideal model, because since we just want to understand the basic interface. Now with ideal model, when we have entered this value, you can see this required input is complete, so this icon is changed. Initially it was half filled red, right? So right now it has been changed. So now we provided the component, we have selected the method also. Now let's say I want to understand the various parameters for this compound, like water, benzene and toluene. So in the Aspen Plus, what you can do is you have this option of retrieve parameters. When you will click into that, it will compute the so Aspen Plus does not display all the properties parameter on the parameter form. When we will do retrieve parameter, it will compute the property and show us as a result. So it has completed and results are available. So if you will see here, in the method section itself, this parameter tab is open. In the parameter tab, under the pure component part, under the result part, you can see for all our three components, whether it's water, benzene and toluene, various data is available. Now again here, Aspen Plus uses its own convention that initially might be unfamiliar with us as we are starting it. So here this thing is mentioned is DCPLS. Now I don't know what does it mean. So again you have to go here and search it. So should be here. Delta Cp by DCPLS is difference between liquid and solid heat capacity at triple point. Okay, so now I understand that DCPLS, what does it mean? It's a difference between the heat capacity of liquid and solid. Similarly, there are various matters, like see, freezing point is easy to understand. For water it's 273 Kelvin, for benzene it's 278, which is around, okay, and for toluene 178. Similarly, this is freezing point. Now you can see the boiling point also, TB. So for water 100 degrees centigrade, for toluene it should be around 353, sorry, this is benzene, 80 degrees centigrade, and for toluene it's around, I guess, more than 100, around 110 or something, yeah, right? Let's say you want to understand what is this MUP. So again use this forum, like search part, and see what is MUP. So you can find this is vapor mixture viscosity. So that is the viscosity of your system, right? So this way you can understand what are the parameters. Under this parameter option itself, you see this pure component option. So when you click into that, so in this pure component, how various properties are calculated, that is also mentioned, like various methods to calculate these properties. So again, it uses its own convention that we don't know of. So let's say I want to understand what is this method KLDIP. So search it. Yeah. So that is liquid thermal conductivity, and you will also get different equations to calculate this liquid thermal conductivity. So that is calculated from here, and the equations to calculate this liquid thermal conductivities are also given, right? Now what you need is different parameters, like this different coefficient values. So when you will go KLDIP1 here, you can find these all parameters which are fitted like in that equation to compute the thermal conductivity with temperature. So this is how to interpret various methods and various properties that are being calculated. So basically you have to explore and understand what each property means. Now depending upon your requirement, you either don't have to go into the details of this, but when you are fine tuning your simulations, you might need to go into the this details, like minute details of your system. Now once we know, like once we have selected components, once we have selected the methods, now I want to understand the change in the properties of my system, right? So in this top menu itself, you have seen, like, see this pure binary mixture, like this options have appeared initially when we didn't had any method selected. Let me see if I can remove it. Yeah. So when I'm not selecting any method, you can see there are no these options are not available right now. But when I'm selecting an ideal model, okay, then I can see, oh, I can see this options are now available. So that help us to analyze the property of a system. So let's say I want to just understand the water property, like I want to see the density variation of water. So when I'm clicking it, one tab has opened, so which is pure component tab. So, and then you can see under analysis tab also, this folder has created with pure one. So pure one is nothing but this system where I want to calculate a thermodynamic property. So there are various list of thermodynamic properties available. Let's say phi is a fugacity. I want to, let's go for the viscosity of a liquid water. It should be MUGHM. CPC. Mass entropy, where it went. Let's say I'm right now looking at the, oh sorry, it's a thermodynamic property. So right now I cannot compute for viscosity. I have to go under transport property, right? So this mu is viscosity of pure component, and then you can specify the units. Okay, so let's say I want to see centipoise, viscosity in the centipoise. I'm adding water, so you have to select this component water, add this component. You can specify this temperature range in between where you want to calculate the viscosity of your compound. Okay, so I have specified it. You can put change the number of interval, you can find the property at specific interval, and when you will do run analysis, system will run and you will get a plot of viscosity with temperature. Now again my point here, like just to again give you introduction, like this is we are going through this interface of Aspen Plus. Nothing is kind of related to I mean it's related to your coursework, but nothing kind of assignment or something like that. So this is just kind of to give you an overall interface of Aspen Plus, so that when you are running it by yourself, you know under which tab to go to find what kind of a property. And since sir has not gone into the much detail of Aspen Plus, I am just giving you a basic overview. It's taking some time again to run. So similarly, like a pure component property, one can find the binary component property, mixture property, solubility. So what we will do, we will also see how to compute let's say TXY, PXY plot, which are useful for distillation calculations. under binary mixture, and then we will move forward with our further examples and assignments. It's taking too much time. I have to change something. So again, meanwhile it's running, let's get back to the PPT part. So sir has already provided a comparison between these various methods, which will be good during what time, right? So I'm again not going into the much detail of it, because from this course point of view, it might not be that much relevant. But if you want to go into the details, my suggestions will be to go through the help manual and understand it, right? After that, once this is done, we will be doing some flash calculations in this part, like these 3 examples we will be solving, and then we will be doing a quiz. Quiz as in which is kind of related to your assignment. I won't be quizzing you guys per se. We have to change that. I guess I have to use some other method for recording, then only it will work. From next lecture on, I will figure it out. Yeah, so you can see it has computed the viscosity with the temperature, and as you know, the with temperature viscosity of liquid will go down, so you can get this property data. If you want, you can zoom into the data, you can zoom out of the data. Like there are various options. You have this show tracker option where you can get the precise value of viscosity at particular temperature. If you want to save this plot, let's say you can just copy it and then you can open your Word or something and then paste it there. Let's see. So you have the viscosity data already present. So this is how you can compute. Sorry. So this is how you can compute various properties. Let's say we have calculated viscosity, then you want to see the density part. So density will be kind of a thermodynamic property. So you have density somewhere here, rho, right? Density of pure component. You can add more than one component also. Let's say I want to study property of both benzene and toluene. So I can add them and I do a run analysis, and then it will plot me out the value of both benzene and toluene in one plot. Now, so this was a kind of a pure component analysis. Let's say you want to do a binary analysis, like 2 component analysis. So as a chemical engineer, for a distillation column design, you must have done calculated TXY PXY plot. Then you must have done that McCabe-Thiele calculation, I assume, to find the distillation stages. So let's say I want to know the TXY diagram, particularly for benzene and toluene, which is the common example people use. Okay. And I want to generate a TXY diagram at specific conditions. So I want TXY diagram, so you can select. I went to the binary part. I'm selecting TXY diagram. I have other options also. Right now I want to TXY. Select the both component. You can provide the mole fraction basis or mass fraction basis. I'm using mole fraction of benzene. Okay, so it will start from 0 mole fraction of benzene to 0.1, and it will take 50 intervals. Now you can specify the pressure value, let's say atmosphere, and I want to compute. So compute the property at, let's say, 10 atmosphere, right? You enter the value and do a run analysis. So it will give you the TXY diagram for both benzene and toluene at 10 atmosphere. Probably this is not. Why this is happening? It should not happen that way. Okay, let it load it out. What we can do, if it will take too much time, then I can move forward with the quiz part, where I have prepared some questions which are kind of related to your assignments, so that you can get an idea of what to do in your assignments. Okay, let's see, wait for 1 or 2 minutes. It's ready. So you can see it has generated a TXY diagram for both like benzene toluene, right? And I can see the various values of mole fraction, mole fraction. So this is kind of a at 10 atmosphere, right? So similarly, you can enter other pressure values also. Now you have, if you want to compute a mixture property, you have ternary mixture. So right now I won't be running any of this property since it's taking too long, but you can add, let's say you have water in your system, you have benzene and all three component. You can provide the flow of them, let's say 10, 5, 5. Okay, it will calculate the fraction on its own, and you want to compute some properties. So under this properties to report tab, you see a new option. If you will click on that, this new item PS1 property 1 will be created, and then you can see there are various properties available for this mixture itself. So let's say you want to understand the specific gravity of a mixture. Select it, add it, and when you will do the run analysis for this particular fraction, between 273 to 373 Kelvin at this pressure value, you will get the property of your system, like specific gravity of your system, right? Now one more thing here, when you have computed this TXY diagram, under the binary part, you should be, or you can also format. So once it has, if you will see, once it has generated this TXY diagram, let's say you want to see XY diagram for that YX diagram or XY diagram, you can click here and then you will get a YX diagram. So this kind of diagram you have used for that McEpthil calculation to find this number of distillation stages for your system, right? so that you can do it from here also. This is just kind of mentioning it. Similarly, as I said, that if you want to calculate a mixture property, you can provide it this kind of input. I'm not running it since it's taking too long to run, right? So this is how you can use this property tabs to calculate various property of your pure component, either binary mixture or a mixture. You can compute this txy pxy calculations. Apart from that, various property computation is also possible if you just need a data collection from an Aspen Plus, since it has this all the data banks. That will be much easier to compute rather than doing it by our own self, right? Now let's say once you have decided your components, you have selected the property, and you are not interested in this property estimation, but rather you want to do a simulation. So go to the simulation tab. When you will do that, if you have any question, you can directly ask and interrupt me, right? I'm not sure what is happening.
Hello.
Yeah.
Can we convert it this graphical form into the tabular form?
The data that we have generated.
Yes.
Let me check. I'm not sure. Let me see. Analysis. Let's say mixture. It went away. It should have some option. I'm just not sure from where. Edit legend should track. I'm not sure as of now, but okay, let me see it and answer you it next time if possible, right?
Okay. Okay.
Thank you. So once you have done a property estimation, you can go to the simulation window, or where we will be doing this process plant simulations, right? So under the simulation tab, you can see in the bottom part you have different models available from mixer, separators, different kind of exchangers, different reactor, different type of reactors, right? And each of this model has set of equation defined within it. So when we will be using them, that's a set of equation will be called, and a simulation will be performed. So let's say right now I will be giving the example of flash drum only. You can see the other aspect, like other columns also. Let's say we have this DWSM, so you can just yes. uh, has anyone any question? Okay, so you can see for as of now we can just figure it out, just see various options. I'm not going into the much detail, like uh, each column has some specific kind of inputs required. So let's say if I talk about the flash drum, so if you will click onto the flash drum, you have to either you have to provide two parameters, either operating parameter of the flash drum, what temperature pressure it works, or you can provide the duty or vapor fraction, right? So this kind of parameter you can provide. So you will need, like, for a set of equations, if you I guess, as I assume you all are familiar with the concept of degree of freedom, that you have number of how many number of sets of equation you have and how many sets of variable you have. So degree of freedom should be zero to get an should be zero of your system to get an exact solution, right? So thus for each of this model you will need specific input parameters. Okay, let's say I want to see this reactor part. If you will click here, again for reactor you need temperature pressure conditions. Same for some other separators. Let's say column, let's say you have multi-frag column. So if I put it here, and if you will click it, the different components that you have to add for that will be given. Like, but this thing we will deal into the later part of the course when we will doing the simulation with this kind of modelers. Right now I'm just want to go give you an overview. So this is kind of a main flow sheet. You can see this main flow sheet again under this view option. Let's say you have closed it by mistake, you can just click go to the view, click to the flow sheet, and you will get it again back, right? uh, when you add a block to the system, you will see here under the block section all the blocks are added. So let's say I remove this B2, I delete it, and then it will go away. So when I'm adding the block, it will be added. When I'm removing it, it will go away from here also. So you can see the various parameter related to block B1, which is flash drum. Right now we have added. So input parameter, the some of the other options are not useful to us as of now. Like you will see, you cannot edit it in them. So mostly we have to deal with kind of what are the inputs related to it and what are the result associated with it. So again going back to the main flow sheet, this is the material stream. So here you can add material, heat, work or power to the system. Let's say I'm right now selecting the material. When you will select the material stream, you will see around the block there are this red and blue marks, right? So this red line indicates the input which is necessary, like you have to provide it, and then blue marks are kind of an optional parameter if you want to provide it. So let's say I'm connecting one stream to the input of the flash. I'm connecting the top vapor product, I'm connecting the bottom liquid product. Select again this cursor, and then you can rename it. Let's say I want to say it feed, I want to say it vapor, like vapor product I want to say vapor, S3 I want to call it as liquid, so you can call it as liquid, right? Now you can see here steam block is like steam folder is also generated where you have all these three streams are present, and for each of them you can see input and result, right? So let's say feed, so you can see here like all these components where this half red mark is like half red circle is shown, which are so these are the blocks or streams where you have to provide an input necessarily. Let's say for both flash drum calculation, I need to provide at what condition feed is coming and what condition flash is operating, and based on that I can do calculate the vapor and liquid fraction of the flash. Thus these two part are not an required condition, like required streams, but these two are. So all when we are using different blocks, presets of data are already defined to understand which inputs will be needed, which are mandatory inputs and which are optional input. Okay, so let's go and let me just go with this example part. So first problem that we will be doing, again this problem is just to kind of give you an overview, nothing related to like moving forward with the course, kind of give you an hands-on feel of the Aspen Plus. And so right, so we have a liquid mixture which contains 60 mole percent benzene, 40 mole percent toluene, which is fed at a flow rate of 100 kilomole per hour, 3 bar pressure and 25 degree centigrade into the flash chamber which is operating at this condition. So applying ideal property, compute liquid and vapor fraction of the vapor composition of this product. So I know you can so I want to specify the feed parameters, right? So from this side panel also you can provide the parameter, or when you will click onto this this feed stream, if I'm doing a right click, I can get the related things in it. So I want to provide an input, so go to the input part. So what I have, I know the composition and temperature pressure. So feed, I'm provide feed is coming at 25 degree centigrade and 3 bar. So temperature I want to provide in degree centigrade at 25, pressure I want to provide in bar, so let's say 3 bar. Molar flow rate I am giving 100 kilomole per hour. Okay, you can provide mass flow rate also, volumetric flow rate, or this flow rate in case of the gaseous mixture if you have. Okay, right now we have molar flow rate. My feed contains water is not there, 0.6 mole fraction of benzene. Instead of molar flow rate, I am doing mole fraction and 0.4% toluene. So when I have entered this parameter, you can see it has converted to the blue tick, like white tick into the blue circle, whatever you call it, right? So that means this input related to feed streams are completed. Now I have to provide the input related to the flash drum. So if I go to the flash drum input, flash drum is operating at 1.2 atmosphere and 100 degrees centigrade. So I want to provide temperature pressure parameter. So temperature, I'm saying it's operating at 100 degrees centigrade, and pressure is in bar. Yeah. 1.2 atmosphere. You can take it bar also, it's fine. So that this data is also complete. So when I have this necessary inputs complete, I can run a simulation, right? If we will go, and if you will do run, it will do a calculation and provide you the composition of vapor and liquid. Now for flash drum, calculations are easy. Like if you would want to put a mass balance and energy balance, that is feed is equal to vapor plus liquid flow rate, and you can do a component balance as well as you can provide in heat balance. So that sample calculation you can do it by your hand also and verify it. Same thing you will get here. Once it is completed, see right now you can see it's showing on the bottom left corner processing input specification. When it is completed, it will show results available. It will take some time. So this problem number 3 I have already dealt with kind of, instead you can try it on your own when you have installed it. So we found the TXY PXY diagram for benzene and toluene solution. So instead select ethanol and methanol. Instead of ideal you can use Wilson activity coefficient model, because ethanol and water mixture is not a ideal mixture, right? And then you can generate TXY PXY diagram as I have shown. Since it's taking some time, I'm not going to solve this here. We will discuss problem 1 and 2 only. Meanwhile it is running, I have some quiz prepared, but we still have time, so we can wait it for to load. Yeah, so it says required input complete. Then it has encountered some error. Warning in physical property system. The following convention component were not in data bank. Processing input. Oh, I guess because of this property estimation, it had made an error. Do I have a result? No. Again, let me rerun it. It's not working well. Let me restart it one more time. This should not happen. We add some properties. Okay, we have added the properties. Let me quickly change to ideal condition. Next. Very good. Simulation part. So then I'm just quickly adding all the data again. So 25. Thousand 10 blocks. To atmosphere. Okay. Let's run it again. So it has run has completed, and now you can see results are available. So when we want to see the results, there are different ways. Like you can see it from this panel also. Like here you can see the result summary, where you can see run status, whether run has completed correctly or not. If there are some warnings, you will get it here also. If okay, this is not an important part. Like this warning is not important, as in If there are some critical warnings, you will see results are available with some error. Okay, if you will click on the stream part, you will get the result for both S1, S2, S3. Like we had specified the data for S1 stream, then S2 and S3 it has calculated. So what is our S2? S2 is a vapor stream and S3 is a liquid stream. So for both vapor and liquid stream, you can see what are the phases they are in. S2 is in vapor phase, this is in liquid phase. Temperature, since flash drum is operating at 100 degrees centigrade and 1.2 bar, both has same pressure value. Then molar fraction of vapor and liquid, you can see it. Similarly, now in if you will see the mole flows of benzene and toluene in both vapor and liquid. So as you can see, molar flow rate of benzene is more, like since benzene is more volatile, more amount of benzene will be present into the vapor fraction compared to the toluene. As you can see, the vapor fraction of benzene in the mole fraction of the benzene in the vapor is more compared to that in the liquid part, right? So this is kind of a simple flash calculation you can do. Now you can customize this flow sheet according to your requirement also. So if you will see here, you can see this modified parameter where you have this different option. If you don't want to show this 3D icon, instead then you can remove it. If you want to show the temperature of stream, pressure value, vapor fraction, so as I'm checking this, all the tick marks, these values are being added into the system and along with the legend. So what does this each of the stream means, right? Same way, if you don't want to provide it, like if you are using this Aspen Plus to generate a specific data and then you want to represent it also, then you can use such option to specify it more correctly, like so that anyone who is interpreting it, they can directly know, okay, what are the temperature, pressure condition, flow condition of various streams, right? So this is kind of a customization option you have here. One more thing here, let's say you want to just see the data associated with the block 1 only. So if you will go into the block 1 and you will see the stream result here, so it will show only the data related to S1, S2 and S3 stream. So right now we only have block 1, but let's say you have multiple component, you have flash drum, then vapor of that flash drum is going into the some compressor and then further it's processing it. When we are seeing the result from this section where you are seeing the stream result, you will get the data of all, but I just want to see the streams related to the my block only, like my flash drum which I am currently interested. So you can go to that block, you can see the stream result of that block. So only streams which are associated to that particular block you will see there. So this is kind of a various way of seeing the results. If you have one more option, like let's say you have wrongly connected any stream, so then when you will right click on that stream, you have this reconnect option, reconnects to the destination, reconnect to the source. So such kind of modifications can be done into this Aspen Plus part, right? So this was the like kind of a overview, property estimation part and the simulation part. Over the next week we will deal into the more of this all the blocks, their relevant calculations, some of the TXY PXY calculation, I think, which I have shown here right now, property estimation. It will be covered in the later lecture of Professor Saha. So if you haven't not exactly got grasp into it, don't worry about it, we will be revisiting it. Right now my purpose was to give you an overview of this Aspen Plus, and I hope I have done a justification to that. Now we can also try this problem too, or we have 20 minutes. Let's see, we can try problem 2 at the end. This is again nothing but instead of two component, I have benzene, toluene and xylene, which are flashed at 1 atmosphere and 110 degrees centigrade with this flow rate under flash drum at this specific condition. So in that I want to compute the liquid and vapor outlet composition. So again, if you want to change any setup, like you don't have to create a new one, you can change the parameter in this only. I want to remove benzene, toluene, and I have benzene, toluene already. I want to add xylene. So let's say I'm adding orthoxylene. So it has found orthoxylene and it has added it. My method is already an ideal that I have selected. I'm just rerunning the property analysis again. You have to just press the next so that it will take you the step by step process. So here what we are doing is like system is at high temperature and then flash drum is operating at relatively low temperature and pressure condition. So according to you, what will happen, like whether we will get only liquid product or vapor product? Can you think about it? Since system contains like feed contains more energy and flash drum is operating at much lower temperature, all the feed should get converted to vapor, right? So that should happen. Let's check it out. Why it has to do this? It's not working. So let's leave it as of now. If it works, then we can come back to again. So what I will try to do is from next time onwards, I will record it in some other PC so that we can perform simulation better here. Sorry from my end for this delay. Rather than, so you guys can try it out this example once you get an access to Aspen Plus. Do install it and learn in software. Like learning in software, any software is like finding and exploring software by your own self so that you will understand more various things, like try out various things. Okay, so these are the simple calculation. If you cannot do it right now, that is also fine. We will be learning again them into the detail part. Okay, this problem 3 is nothing but generating an TXY diagram, kind of a property estimation that we did, right? So now since it's taking too long and we are running short of time, let's move to the quiz part. So this I will need answer from you guys because this is kind of an related to assignments that you guys have to submit. Okay, so this assignments I have seen it's kind of related to the questions that you learn in all in the week 1. So first question I want to ask, like what is the full form of Aspen Plus? I had just informed you in the starting part. Do anyone of you remember? Hello, guys, I will need answer from you this time. Let's say you have forgotten it. So it's like advanced system for process engineering. So that's a full form of Aspen Plus. Aspen. Now, what kind of a approach is used in Aspen Plus?
Equation oriented.
Not exactly. It uses sequential modular approach. So in Aspen Plus, calculation are done by sequence. Like first one module will be computed, like a mass and energy balance of block 1 will happen, then block 2 and block 2. So that's a sequential modular approach. Equation oriented approach is for some other model of the Aspen Plus where you specify your own set of equation to compute various things. So answer is sequential modular approach. Now when we were looking, like when we were adding the compounds, so other than the compound name, what other criteria I can use to find the desired compound? There were 2 properties that we had mentioned, right? If you are not
It
able
means
to, yeah.
contain and begin with.
Contain and begin with is again related to the compound name, but apart from that, there were 2 properties that we can provide a range of that properties. One was molecule weight, and can you remember the other part?
Boiling point.
Boiling point.
Boiling point.
Yeah, so that's a molecule weight and the boiling point. Now, which of the following is not a virial equation of state? Which of the following?
NRTL RQ.
Yeah, NRTL RQ. Okay, so no, sorry, unifag method. NRTL is again, NRTL RK is an equation state, like virial equation of state. So let's see if you get confused in this. So this is just a interaction session, so it's fine. But for your assignment submission, just be thorough what you are answering it, right? Now, question 5, like which of the following method is used to determine the electrolyte property? Now, yeah, if any one of you know the answer, then can say it, or I will answer it. So let's say you don't know the answer, but at the same time I also don't know. So what you have to do is again. Hello. Huh. So go to the method parts. Okay. So question says like which of the obviously you have answer here, but let's say which method is used to determine the electrolyte properties. Okay, then as I was saying, we have this method assist, right? You can use this method assist, specify component type. We want to see an electrolyte, right? So here you can see the electrolytes under special compound, it's present. You have electrolyte system. So these are the various models, ENRTL RK, ENRTL SR, Pitzer. These are the different models used to calculate the electrolyte properties. And does our option contain this? So I have and A and B. So that's my answer. So in case, like again, the way I have prepared this question is so that you guys should get used to the search feature of the Aspen Plus, so that you understand various properties and use of different models. Now, which of the following parameters are needed for mass and energy balance? Now, when I see, don't know about you guys, but when I see this parameter, I don't know meaning of any of it. Like these are the terms used by Aspen Plus. Okay, so again you have to just simply search it. Like I have this first part, right? So if you will go into this search help part, and by the way, these are the previous year's assignment questions, so I have not generated it by myself. Like some of the questions are related to that. Okay, so see, you get this vapor pressure. So vapor pressure is represented by this this format, like the extended Antoine equation parameter, and you can get the equation from that also. Okay, so that is a vapor pressure. Is vapor pressure is needed for mass balance? Yes or no? Let's say I want to do a flash calculation, it's needed. Then I have CPIG. CPIG we already had searched, it's kind of a heat capacity. Then you have this part, DHVLWT. Now again I don't know what that is. So if you will do a search, yeah, that is heat of vaporization. That is obviously needed when we are doing a heat balance calculation. But this part, option D, what does it say? It is RKS KBV. So this is some sort of a equation of state method, and that is not needed, like that is not a parameter, right? So it's a method. So your answer is ABC. Similarly, which property method is used for a free water phase approximation? Now I have shown you particularly at low temperature and moderate pressure, so I expect an answer from you. Like we had seen various properties for water which were available. So which method do you think will be more usable here? Any guess?
Ideal.
Yeah, since we are working at low or moderate pressure, and all the other property that we have seen, they were looking at the higher pressure values of the water, right? Now, in the Aspen Plus, how we know that required input is completed? So which of this property indicates that? This should be easy to answer.
White tick in blue circle.
Yes, so that's the correct answer. So what are the different colors option here? So if you have that half black circle, sorry, half red circle, that means required input is incomplete. If it's completed, it will show a white tick. If you have this again, so yeah, this kind of a symbol, like okay, let's come to the question 11, then I will discuss. Apart from that, you can see, like, observe this various icons also, that all will also help you to identify where the error has occurred. Now, question number 9, which of the following module is not part of the separator model?
Crystallizer.
Okay, crystallizer. Only crystallizer? So actually this F split is also not a part of a separator model. That is some filtration unit. So mainly flash 2 and decanter are the part of the separator. Now the red color stream in any model will show a required input or output is required. So is it true or wrong? For a block, if it input and output stream are indicated by red color, is it required input or optional input? We had discussed this, right? So you have two options when
Required input.
required input. So answer is true. Now when you see this kind of a yellow symbol on any of the value, like what does it suggest?
Result with warning.
No. So result will warning will be shown
Input
by,
inputs are changed.
yes. So inputs are changed. So now you have to again new results are not generated. So you have to rerun the simulation. Then you will get a new result. Okay. Now this is an example. Just first read the problem statement. You have mixture of water and methanol at 50 degrees centigrade and 1 atmosphere. Okay, that is specified by this S3 stream. So these are the specification that we have to put. So first question is, like, what will be the value should be indicated by A. So here we see the molar flow rate of water, which is given as 1. So what should be the methanol flow rate? We have composition. Water is 25 mole percent, so methanol will be
3.
3, right? And this missing data, like the temperature value, what should be the temperature value? It's simple, like 50 degrees Celsius.
50 degrees Celsius.
So we have to put it in Kelvin though. See, unit also will matter, right? So it's 323.15 Kelvin. Now, which of the model is suitable for equilibrium calculation? Actually, I wanted to, this problem 2 itself would have answered this, but from flash drum calculations also, the flash drum block is suitable to do an equilibrium calculation. If you want to find the dew point and bubble point, this flash drum will help. Let's see if that simulator is working. I can go back and show you how we can calculate dew point and bubble point through flash drum. Which type of block is used to represent cyclone separator in the Aspen Plus? So cyclone separator will come under which category from this? If you have seen it. Let's see, let me go.
Solid separator.
Yes, solid separators. Now, which of the following property cannot be calculated directly in Aspen Plus? So you have various properties. When we simulate the result, we get a stream data, right? So which of the properties not calculated? Like it's not available directly. So
Entropy.
no, it's actually Gibbs free energy. So if I show you results available with warning, just so it had some error, right? Just quickly run it. No. So actually, when you will see, when we have this stream data available, when it's computed, so Gibbs free energy value is not mentioned. For that, you have to do that in property analysis. You can calculate it, but in this simulation analysis, you won't get the Gibbs free energy. Rather, you will get enthalpy, entropy, and heat capacity. What is the purpose of flash block in the Aspen Plus? It should be easy, right?
Separate mixture into 2 4 more phases.
Yes. So that's the correct answer. Now, which type of thermodynamic model is used to calculate the phase equilibria? Like,
Rolls law.
yeah, Raoult's law. The term CPI GDP, this is associated with, I think we have looked into that, if you remember. All else not, if you don't know, then what you will do? You have to just search it in the Aspen and you will get
Help
the
button.
sorry?
Search in the help button.
Search in the help button. So if I do it, CPI GP, right? CPI GDP. So that's a general component, ideal gas heat capacity. So it's an heat capacity. And which model will suit more for a non-ideal liquid mixture? Equation of state or activity coefficient model?
Activity coefficient.
Okay. So, so your assignment 1 question, these are also kind of related to this small MCQ question only. I mean, half of the things you don't have to memorize it. Like, no one is going to ask what CP IGDP means, or where exactly is cyclone separator present into this block, right? But the idea here of this assignment is so that you can understand, you explore the software more, so that you understand various things, right? So get familiar with the software, nothing else. So do solve assignment 1. I think you guys have 2 weeks limit, right? So assignment 1, if I'm right, it's due on 8, somewhere around 6 or 8, right? Can anyone confirm?
8.
Right. So some of the questions are related to this way only, and if you don't find an answer, like go and search in the Aspen help manual only, you will get some results. See, here results are available. So what I was showing you is, that's a stream result. So here you will see you have molar enthalpy, molar mass entropy, you also have enthalpy flow rate, but you won't have this Gibbs free energy. So this question, like what property is not directly calculated? It's Gibbs free energy. Okay. I think the CP should be here. Oh, it's not there. Anyway, so these are some of the questions, and this was the general overview of Aspen Plus. This problem 2 is still remaining, which I wanted to show you guys. If it's work, we can do it right now. In the stream result, now just let me recheck the input. So we have 110. So we have mixture of benzene, toluene, xylene at 110 degrees centigrade and 1 atmosphere. 1 atmosphere with a flow rate of 100 kilomole per hours, and the mole fractions are 60, 30 and 10. So let me add it, 60, 0.3 and 0.1. Then flash drum is operating at 1 atmosphere and 80 degrees centigrade. So 1 and 80. So I have changed the input, and if I run it, result available. So you can see here what has happened, that our feed that was at 110 degrees centigrade and 1 atmosphere. Okay, so here unit is bar, you can change it to atmosphere also. 1 atmosphere, it's completely converted to liquid phase. Okay, and there is no vapor fraction generated. Why? Because see, the flash drum is operating at much lower temperature at 80 degrees centigrade. So your output is only liquid, you don't have any vapor fraction. Now repeat the same calculation at 1.5 atmosphere and 120 degrees centigrade of operating condition of flash drum. So if I do that, 120 degrees centigrade and 1.5 atmosphere, right? This condition, and if I rerun it, so result completed. What you will see the results is now you are getting only vapor product. So what is happening is that at 80 degrees centigrade of operating condition of the flash drum, you are getting only liquid well, and at 120 degrees centigrade you are getting completely vapor. So what does this indicate? That, can any one of you guess? So this shows that like 120 degrees centigrade is way above the dew point of the system, like dew point of your mixture. Thus you don't have any liquid product present into the system, right? So if you will see the stream, everything is converted to the vapor, and your temperature is 120 degrees centigrade. So what is dew point? Dew point is temperature where you will get first liquid droplet, right? So your 120 degrees centigrade is way above it. So now let's say I want to compute the dew point of this system. So apart from that property analysis, like in the property estimation video show, we can also compute the dew point with the help of flash drum also. So let's say instead of providing temperature pressure value, I provide a vapor fraction. Okay, so I have to write a vapor fraction that I want to get all the feed being converted to the vapor. Then, and when I run it, so what it will do, it will compute me the properties, like it will compute the temperature where I will get complete fraction of vapor. So see, temperature is at 118 degrees centigrade. So at 118 degrees centigrade is a dew point for the mixture of this benzene, toluene and xylene at this specific composition. So this is how you can also use this is how also you can use this flash drum to calculate the equilibrium property. That's why I had that question put it in, that which of the component is used to calculate the equilibrium property, right? More of this we will deal into future also. So this was just to give you an overview, an idea what we can do with this Aspen Plus. So now any of you has any question, we can take it, else we can end the session. So was it useful, as in you guys got an overview, right?
Yes, sir, it was useful.
Yes.
So
Yes, sir, it was useful.
okay, thank you. So just try it out. I think you must have received the mail for Aspen Plus installation. Install the Aspen, try various things. So just get used to that software, and then we will work on to the various bigger problems in future. Okay. So that's it. Now you guys can leave. I will stop the recording. So for PPT part, both the recorded lecture and the presentation, you guys will get a link. So I will upload this on YouTube also, so you will get the YouTube link, and for the presentation we will share a Google Drive. So on the Swayam portal itself, there will be one tab created for live interaction session classes. There you should get it. Okay. Yeah. Okay guys, so I'm stopping the recording. Thank you for joining.